Okay, so let's say we have the wall with the two narrow slits in it, and then somewhere else further out, we have another wall that we're casting the light onto to create this pattern. And if there were no other modifications, what would you expect to happen in the center of the pattern here? If we're talking about a spot that is exactly in line with the midpoint between the two slits. Like we've got this path of light from the top slit and this path of light from the bottom slit. What would you expect to happen at that midpoint there?
A bright spot?
Yeah, and why would that be a bright spot normally?
Because there's no phase constant difference.
Sorry, there's no what?
Phase constant difference.
There's no phase constant difference. And also, what do you notice about these two paths?
It's the same.
They're the same length.
Right, same length. In other words, there's no delta x at all at the center. So at the exact center, there's no delta x, and also there's no phase difference because the light's just getting through both of these slits in the same sort of way. So that would mean that you'd get no difference at all between the two ways. There's no, the total phase difference is 0, and that means constructive interference. So you've got a bright spot. But let's say we modify that by putting in this crystal on one of the slits. And that causes a phase difference of exactly pi. So now we have, at the center, we still have no delta x, but a phase difference of exactly pi. Delta little phi equals pi. So there's no delta x at the center because these two paths are still traveling the same distance, but there is a delta little phi that's equal to pi. So if you combine those, 0 delta x plus pi worth of delta little phi, what do you get for the total phase difference there?
A pi.
And what type of interference would that be?
Constructive. Oh, sorry, destructive.
Right. So with this crystal in place, we now have destructive interference at the center. So the center is going to be a dark spot. Any questions on that so far? And let's say we look at the next spot where we get a bright spot. So the exact center is going to be a dark spot. If we shift up to the next bright spot, we mark that as a dark spot. But let's say we want to look for the next location beyond that that is at a bright spot. And we consider the two path lengths to that location. So this path length and this path length. At this location, would we still have no delta x?
No.
Right, it looks like these two paths are traveling different distances. So here there is a delta x. We also still have delta phase shift equals pi because we're still talking about a slit with a crystal and a slit without a crystal. But we want this to be a bright spot. So to be a bright spot, what do we have to assume about the total phase difference?
It has to be an even number.
Yeah, it has to be even.
Sorry, it has to be what?
Even number
Yeah, it's got to, well, specifically an even number of what?
of pi.
Even number times pi, yeah, because that would be a whole number of cycles. But we already have delta little phi equals pi. So how much do you need to add to that to make it a whole number of cycles?
Another pi to make it 2 pi.
Yeah. For the total phase difference to be 2 pi, we need an extra pi from the delta x term. And specifically, that'll be from the 2 pi delta x over lambda. So we can say we've got an extra pi from 2 pi delta x over lambda. In other words, we need 2 pi delta x over lambda to equal pi, or really any odd multiple of pi, but I think 1 pi is going to be the easiest to use if we want the smallest distance from the center. So if we try that, if we want 2 pi delta x over lambda to be 1 pi to balance out this 1 pi from the phase shift difference, what would we need delta x to equal?
Lambda over 2.
Sorry, what was that?
Lambda over 2.
Yeah, lambda over 2 should work. Because we can cancel out pi, divide both sides by 2, we get 1/2, multiply by lambda, we get lambda over 2. So that means in order to get the very next bright spot beyond the dark spot at the center, we need delta x, the difference between these two path lengths, to be exactly lambda over 2, half a wavelength. And note that without the phase shift, if the only difference between the waves was a path length difference of lambda over 2, what kind of interference would you expect that to be? If the two waves are half a wavelength offset. If that was the only difference, what kind of interference would you expect there?
Is it destructive?
Destructive.
Yeah, half a cycle offset, if that was the only difference, would be destructive interference. So this is a spot that we would usually expect to be dark because of the location. But the location of half a phase offset or half a cycle offset, plus the extra phase shift difference from the crystal of an extra half cycle, that's half a cycle offset because of the location, plus an extra half cycle offset because of the crystal. That makes for a full cycle offset, and that's essentially no offset at all. So that's constructive now. So this will be a bright spot, as long as the difference between these two paths is exactly half a wavelength. Any questions on that so far?
No question.
And do you have any geometric formulas for how we can relate delta x to other distances or angles here in the double slit setup?
Delta x equal d times sine theta.
Yeah, we could use from the geometry, delta x is d times sine theta. So that's going to look like, here. So also delta x is d sine theta based on the geometry of the situation. So we could set lambda over 2 equal to d sine theta. However, this one's not really talking about the angle involved. We know we know d, we know the distance between slits, 7.5 times 10 to the negative 5 meters. But we don't know the angle. Instead, we know that the bright spot is 1.5 centimeters above the dark spot at the center. So if all we know is the vertical distance, you have another formula for delta x, a variation on d sine theta that relates it to the distance instead of the angle.
Is that the delta y over big D?
Yeah, that should do
equal
it.
to-
And that's ultimately just from geometry, because from geometry again, because if you take this distance, which we usually call big D, That is just the, in this case, horizontal distance from the center of the slits to the center of the pattern. So this distance here. And then if you also take the vertical distance, which we could call y or sometimes delta y, I usually just think of that as y because it is the y coordinate if we treat the center point as 0. And then if we also draw in the hypotenuse of that right triangle, formally theta is the angle between D and the hypotenuse here. So we can fill in theta there. And in this right triangle, what trigonometric function would relate y and big D and theta?
Tan.
Yeah, tangent will work because y is the opposite side from theta and D is the adjacent side from theta. So we can say tangent of theta is y over big D. However, the formula we have for delta x is involving sine theta, not tangent of theta. But sine theta would be the hypotenuse, would be y over the hypotenuse. And if this is a very narrow triangle, the hypotenuse is almost the same as side big D anyway. So we can say that for a very small angle, tangent of theta is approximately sine theta anyway. Sine theta is approximately equal to tangent of theta. And we can use that here. In fact, it specifically says you can use the small angle approximation. We can replace d sine theta with d tangent theta. And tangent of theta is y over d. So delta x is d times y over big D. Little d being the distance between slits, big D being the distance to the wall. And I think we know a lot of these. In order to get the first spot of constructive interference here, we need delta x to be lambda over 2. So we can fill that in. And combining all of this information, we get that delta x, which has to be lambda over 2 to make this work, must equal d times y over big D. That is, the path length difference formula we get from geometry has to match the value of path length difference we expect from the idea of interference. Any questions on that so far?
For the delta y, does that necessarily have to be, let's say, if the center is the bright spot, does it has to be the difference between the center bright spot to the next bright spot, or can it just be the bright spot to the dark spot next to it?
Well, the thing is, if you're talking about spots fairly close to the center, they're going to be evenly spaced or almost evenly spaced. Further from the center, they get more noticeably spread out. But according to the small angle approximation, near the center, the spots should be pretty evenly spaced. But formally, what we're talking about here is from the central dark spot to the first bright spot above it. However, if you did take a look at like the next dark spot beyond this and the next bright spot beyond that, those should be spaced about the same distance apart from each other as these ones are. And likewise, if you go downwards instead of upwards, they should also be equally spaced. You're going to get an alternating pattern of bright spots and dark spots that are pretty close to evenly spaced. It's not truly evenly spaced. The idea that they're evenly spaced is based on the small angle approximation, which isn't truly real, but it's very close to reality. So we can say that the bright and dark spots will be very close to evenly spaced, but that gets less and less accurate the further you get from the center. Any other questions on that so far?
Sorry, Casey, I still don't get it because I thought delta y is, let's say on your screen, that is like the center is the dark spot, Because like initially I thought delta y is like from that dark spot to another dark spot.
Well, y is just the vertical distance from the center to whatever spot we're talking about. In this case, the spot we're talking about is the first bright spot beyond the center.
Okay, so it can be anything that we are looking at.
Yeah,
It
yeah, it's
depends
just
on what angle we're looking at.
right. It's ultimately the y value here is just the coordinate system. Y just represents the vertical distance to whatever spot on the wall we're currently talking about.
Okay.
And we're currently talking about the first bright spot beyond the central dark spot. So that distance, specifically the 1.5 centimeters given, is that distance for the first spot where we hit constructive interference.
Mm-hmm.
And within this equation, what are we trying to find? What's the only unknown left here?
I think we're trying to find lambda, right?
Yeah. Yeah, the ultimate question here is what's the wavelength of the laser? And I think we know the rest. We're given the distance between slits, that's 7.5 times 10 to the negative 5 meters. We know the height of the first bright spot, that's 1.5 centimeters. You'll probably want to write that in meters. Not necessarily have to, but probably a good idea. And then capital D is the 4 meters of distance from the slits to the wall. So I think we can just solve for lambda by multiplying both sides by 2.
Casey, since I'm the one who asked this problem, I don't have any problem like solving for lambda. So for like the sake of saving time, we can move on if no one else have the problem with this.
Yeah, that's fine. Multiply those out, make sure the units match up, and that should give you a wavelength. Anyone else have any questions on that one? Okay, then yeah, let's move on to the next one you sent in. Quiz 2 here.
Yeah, sorry, I didn't mean to interrupt. I didn't know it was gonna send right when I was trying to upload it.
Yeah, that's fine.
But I was just struggling with like the conceptual, like I feel like this was a very conceptual quiz.
Mm-hmm.
I was wondering if you could like go over like how to solve or how you would work through questions like this.
I think this one's actually going to be pretty similar to the setup we were just looking at. That
yeah, it's a slit experiment.
Yeah, we've got the double slit experiment. And without the device, we get bright spots at certain locations, including the exact center. And with the device, the center is now dark instead. How did we accomplish that in the example we were just looking at?
Is it because the bright spots don't change because they're physically spaced still the same, that it's just like a phase change?
Yeah, we're still talking about the same locations. So the locations haven't changed, so that means the delta x's are still the same as they were. So for instance, the exact center still has delta x equals 0 because the two paths are going the same distance to get to that location. So what's the only other part of the total phase equation that could change there?
Well, we know that they're the same two sources, so it would only be a phase change.
Yeah, we could have a difference in phase, specifically the phase constant or phase shift. Mm-hmm. And since it's saying we're adding a device to one of the slits, which modifies the wave in some manner, presumably that device is creating a phase change or phase constant shift. And presumably, how much phase shift would you need in order to change what was a bright spot into a dark spot?
A half a phase to keep it out of phase?
Or I'd say half a cycle. And how much is that in radians, half a cycle?
Pi.
Right. So presumably this device is just giving an extra plus pi to the phase constant of one of the waves. That means that the center, for instance, which has no path length difference, and previously had no phase constant difference either, so it was bright. Now that has still no path length difference, but it has half a cycle of phase constant difference. So that makes it dark because now the total phase difference is pi. And you can also see this with the other locations. For example, let's say this location here was a dark spot because the path length difference was half a cycle, presumably, half of lambda. That same location is still offset by half a cycle worth of distance, but now there's also half a cycle worth of phase constant. So that means half a cycle and another half cycle is a whole cycle. So what kind of interference is that now? If you got half a cycle worth of distance and half a cycle worth of phase, what's half a cycle plus another half a cycle?
One cycle. So it's this one cycle. One cycle.
One
You're
whole
talking
cycle
about,
would be what kind of
one
interference?
cycle is like 2 pi. 2 pi
Right.
is constructive.
Right, and that's why we get a bright spot there. So with that extra plus pi, that extra plus half a cycle, everything that was a bright spot becomes a dark spot. Everything that was a dark spot becomes a bright spot. So no compression or stretching of the pattern. We're just changing everything that was a bright spot becomes a dark spot. Everything that was a dark spot becomes a bright spot. Because we're not changing the path length difference at all. We're also not changing the wavelength. We're not changing any of the distances. All we're doing is adding an extra half cycle to everything.
So when you say you're not changing the path length difference, that means that you're not changing the wavelength of
well, those are two separate things. The wavelength is the color of the light. So if we're shining this red laser 600 nanometers onto the slits, and then we continue shining the same red laser onto the slits, the wavelength is still the same because it's still coming from the same source. The path length difference depends instead on the location. Like each location has a certain difference in path length. Like if we were to draw out the slits here,
oh, so path length is X.
Yeah, old delta X.
Okay.
So for instance, with the spot I've circled in green here, if we were to draw out the paths to that location, we'd have this path and this path. And those paths are not the same distance. There's some small difference in how long those paths are. That difference is delta X. But if we take the same setup with the device, this same location is still experiencing the same delta X, the same difference in path length. Because we're still talking about the distance from one slit to that location and the distance from the other slit to that location. So if we're looking at the same spot on the wall, we still have the same delta X, the same path length difference. We also still have the same wavelength because we're still using the same color of light. The only thing that has changed is this device that's causing an extra plus pi worth of phase shift difference. Nothing else will be changing. Any other questions on that one?
Yeah, I think I'm still struggling. So, okay, so you said you're looking at the same spot of the wall, so you know that you'd have the same change in X. So that means the middle term would be 0. But then the period wouldn't change even if you had different light. Like if you had a different color of light, that would cause it to change, right?
Well, not really, because the thing is if you take a look at those deltas here, the delta isn't talking about comparing before the device versus after the device. The delta is comparing one of the paths versus the other path. So one of the paths and the other path with the device, or comparing one of the paths and the other path without the device. So these deltas aren't talking about with the device versus without the device. The deltas are comparing one of the paths versus the other path.
Okay, so then, like if you were to say have a slit where one slit was radiating blue light and the other slit had red light, then you would have a change in period?
Yeah, and that means that this term would be non-zero.
Okay.
At which point that would really be the most important term, because that's a term that depends on time. So if you have a non-zero difference in frequency, if you've got two different colors of light, that means that the type of interference you get changes as time passes. And what do we call that if you have different frequencies leading to different interference as time passes?
Beats?
Yeah, this would be beats, just with light instead of with sound.
Oh, okay. Okay, and then again, can you go over how, so you know that it's not going to be either compressed or stretched out, because if the pattern was to be I guess my question is, what causes the pattern to be stretched out or compressed?
I think the only way you would be able to accomplish that is by changing the wavelength, like if you swapped the light for a different color. Because if you take a look at the rest of the equation, like let's say we ignore the phase shift difference for now. Because if you add phase shift, that's just changing everything that was a bright spot to a dark spot, and everything that was a dark spot to a bright spot. So you're flipping everything, but you're not compressing or stretching it at all. You're not changing the distances. You're only changing which locations are bright versus dark with an exact swap.
Okay.
Let's take a look at what would happen if, let's say, assuming we have no phase difference at all. And of course, we can ignore the frequency term as well, because these are the same frequencies. And since they're the same wavelength, we can factor wavelength out of the delta there. So we just have delta x over lambda. And let's say we're looking for bright spots. If we're specifically looking for a bright spot, what does delta total phase have to be?
An even number, even pi.
Yeah, even multiple of pi. In other words, 2 pi times n. That is a whole number of cycles. And if you solve this for delta x, what do you get?
Delta x, you get negative n over wavelength equals delta x.
It's already divided by wavelength though. So how do you undo divided by wavelength?
Oh, my bad. Negative n times wavelength.
Yeah. Also, since n can be any integer, whether positive or negative, attaching a negative sign doesn't really matter here. We can just say n times wavelength and treat it as n could be a positive or negative number. It doesn't really matter which. In any case, whether it's positive or negative really just depends on the order you're subtracting anyway. But generally, to get a bright spot, you want a location where the difference in path length between one wave's path and the other wave's path has to be a whole number of wavelengths. This is, of course, assuming this is without the device. With the device, you need something and a half wavelengths instead. But without the device, delta x has to be n times lambda. And from the geometry of the situation, what formula did we get earlier for delta x?
Can you get like delta x equals like wavelength times big D over change in y? Something like that?
I think the other way around. Delta x was, I think that ended up being d times sine theta, which also ends up being d times y over big D approximately. Because it's d times sine theta, but sine theta can be approximated as just distance along the wall divided by distance from the slits to the wall. So if we combine these, we would get delta x being n lambda, also being dy over big D. We can set those equal to each other. And let's say we want to know what heights on the wall, what y values the bright spots appear at. Can you solve that for y?
Yeah, n times lambda times big D over little d.
Right. And if you go up and down the wall, lambda, big D, and little d are all constants.
Mm-hmm.
Which means the bright spots are just going to be a whole number of multiples of some constant distance. In other words, the bright spots are evenly spaced. So like from the center to the next bright spot is going to be some distance. That's 1 times lambda times big D over little d. To the next bright spot is going to be 2 times lambda times big D over little d. Then 3 times lambda times big D over little d. So these are going to be evenly spaced because they're all multiples of the same small distance. And again, this is using the small angle approximation. It's not truly accurate, but it's pretty close to accurate as long as you're fairly close to the center. However, what does this constant depend on? Because we get y equals n times a constant, but what values go into making up that constant?
Y?
Well, y is the result. Y equals n times a constant. But what is that constant?
Any integer?
Sorry, what was that?
Any integer?
That's n. But what's the constant that n is being multiplied by? If we backtrack to where we got that in the first place, what do those values represent? I think it might be easier to see if I actually draw this out. Let me clear this. Let's say we have the wall that the pattern is appearing on. We're going to get a bright spot in the center. The central maximum. And then some distance beyond that, we're going to get the next bright spot. And then the next bright spot. And also below that as well. If we label the heights of these on the wall, we can say the one at the center is y equals 0. The next one up, since n would just be 1 for the next one up, we get y equals 1 times lambda times big D over little d. And then the next one beyond that, we plug in 2, so we get 2 times lambda times big D over little d. Or if we're going downwards, we'd have -1 or -2. And that's what I mean by evenly spaced. The distance from the center to the next one up is lambda d over d. From the next one up to the one beyond that would be another plus lambda d over d. Or as we go down, the distances are always lambda d over d. So these bright spots would be evenly spaced on the wall.
Mm-hmm.
Any questions on that so far? But that spacing, the distance between these, that distance is lambda d over d.
Is it? Yeah, never mind. Yeah.
So is there any, sorry, go ahead.
No, it makes sense because that's what y equals.
Right.
Wow.
So y would be n times lambda times big D over little d. The difference between these, though, the delta y from one to the one bright spot to the next, would be the lambda times big D over little d, from 1 to 2 or from 2 to 3 or whatever. Is there any way we could change that? Is there any way we could make these bright spots further apart or closer together?
Couldn't you make like the screen farther away from the slit?
Yeah, if you take the screen further away from the slits, that's increasing big D. So that means the delta y would be larger. The spots would be spaced further apart. So moving the screen back and forth changes capital D and therefore changes or stretches or compresses the pattern. What else would have that effect?
So we can change any of those values. We can change the lambda, we can change the small d.
Yeah, so for small d, for instance, if you take those two slits and make them further apart or closer together, that will also change the pattern. So if you have some sort of flexible material, if you can take those two slits and stretch them further apart or closer together, that will change the pattern. Still the same overall shape, but different proportions. But lambdas, I think, is really the one we want to look at here. If you change lambda, that will also change the spacing of the pattern. It'll still keep the same general shape, but get stretched out further apart or closer together. And what does lambda represent for light? What would you see differently about different wavelengths?
Different colors.
Right, different wavelengths of light are different colors. Red light, for instance, is a fairly long wavelength. Whereas if we take a look at blue, for instance, blue is a much shorter wavelength. So let's say we have blue light. If you're using blue light instead of red light, the wavelength is shorter. What does that tell you about delta Y?
Be shorter.
Yeah, we'll have a smaller delta Y. However, what location still has to be a bright spot?
The center?
Yeah, the center is still going to be a bright spot. So the center, if we use blue light, the center is still going to be a bright spot. But the next bright spot, n equals 1, is going to be closer. It's going to be less further away. And then the next bright spot beyond that will be the same equally spaced distance. So we might have, let's say, see if we can get those the same distance. Yeah, something like that. So we'd have, this would be n equals 1 for the blue light, and then n equals 2 for the blue light. And then we could also go in the other direction. Evenly spaced in the downwards direction, we'd have n equals -1, and then n equals -2, something like that, for blue light. But then if we go somewhere in between, maybe halfway between blue and red light would be, let's say, probably greenish light, I think, yellowish greenish. So if we have some yellowish greenish light, that's going to be halfway in between. Again, the center is still going to be a bright spot for the yellowish greenish light, but the first bright spot is going to be somewhere between the red and blue ones. And then the second bright spot is going to be somewhere between the red and blue second bright spot. And likewise in the other direction, we'd have yellowish greenish somewhere between red and blue. And then the second green spot is going to be somewhere between the second blue spot and the second red spot. And then we could fill in other in-between values as well. Between red and green, we presumably have maybe some yellow and orange, which will also both be existent at the center.
Does this also explain why in one of the FNT question, they ask us why the blue is the closest one that we see?
Yeah, it looks like we end up with, if you've got these colors that are sort of smeared out, what's it actually going to look like?
What was the question again? I'm sorry.
What does this actually look like? If you have a bunch of colors that get smeared out.
Smeared. Is that like the white light?
Well, white light would be if all the colors are together. So at the very center, all the colors together are going to be white light. So at the center, you're going to get a bright white spot.
Mm-hmm.
So at the center, all the colors hitting together form bright white light. But then if they're smeared out, you get like red, then orange, then yellow, then green, then blue. So what would you actually see here? What does this look like?
A rainbow.
Yeah, this smears out into sort of a rainbow pattern. What you end up with is this bright white spot at the middle, then a gap of darkness, and then a rainbow that's a little bit spread out, and then a smaller gap, and then a more spread out rainbow. And it's getting more and more smeared out. Eventually they start to overlap and it kind of blurs together. But you get this very bright spot in the center, then a very dark zone, and then rainbows spreading out from there. With blue closest to the center, because that short wavelength means a small gap, a small difference from the center to the first bright spot. Any other questions on that? All right, then I think that's it for now. Let me know if you have any other questions, and I will see you next time.
Thank you.
You're welcome.